Very good morning. Yeah. So last time we have done mean value theorems, and mainly was Rowe's theorem and fundamental mean value theorem. So now we are going to look at their applications. Okay. So the very first application of the mean value theorem is that if a function derivative is zero inside a open interval AB. So once you say f is differentiable, means it's automatically, obviously it is continuous. Okay, so if f dash of x is 0 for every x in open interval AB, then f must be constant. And it's a very simple application of mean value theorem. So if the function is zero function, you no need to show anything. Okay, so function is non-zero function you are taking, and let's take the interval a2. You take any choose point x in I. You choose any point x in I. Now consider this interval a2x. Then since f is continuous on the closed interval I throughout the interval ab, so it also continues on the interval a2x. Further, f is differentiable on the open interval AB, so it also continues on the interval open a comma x. Okay, since x is a point of I, it will never cross the B. Okay, so these satisfy both the condition of mean value theorem, fundamental mean value theorem. So it gives you guarantee that there must exist a point C. So C must be depending on x. So that's we are denoting by C suffix with x inside this interval a to x, such that f dash of C is equals to f of x minus f of a divided by x minus a. Now since it is given that f dash of x is 0 for x belongs to a to b, open interval AB, and C is a interior point of open interval ax. Okay, so that condition implies that f dash of C must be 0. Okay, and since you are assuming that x is here, x is strictly greater than a. So we are assuming that x is strictly greater than a. So then, but f dash of C is 0. So then what will happen is, so f of x must be equals to f of a to accommodate this condition f dash of x is 0 for x in open interval AB. Okay, so this implies that f of x equals to f of a throughout the interval a to x, which you have started with. Okay, so if function is a zero function, that's not a problem. Function, if it's not non-zero function, then you can show by using the mean value theorem that f of x is equal to indeed f of a. Okay, indeed you can show that f of x equals to f of b as well. Okay, so because it remains constant values, it doesn't matter f of a or f of b. Okay, so then you can work out the problem with, instead of working with a to x, you can work with the problem to x to b. Okay, but still this condition implies the fact that for every x in AB, f dash of x is 0. So whatever the point inside interior point of the interval, open interval x comma b, such that f dash of C is equals to f of b minus f of x divided by b minus x. So certainly we are choosing x strictly less than b here. Okay, so that will meet this condition only when f dash of Cx is 0. So that will imply f of x equals to f of b. So it's entirely a constant function. What is the immediate application of this result? This result, what you have just learned, is whenever you have two functions f and g, both are continuous on the closed interval I and differentiable on the open interval AB, and they are so that their derivatives are identical, means like f dash of x and g dash of x are same. Then in that case, f and g are differed by only constant. Okay, so this is what another application of mean value theorem. Okay, so this result immediately implies that, so if all the conditions are true, you have this uh, let f and g are two functions defined on the closed interval I, where I is a closed interval AB, and are such that the very first condition is f and g are continuous on closed interval AB, that is I. And second condition is that f and g are differentiable on open interval AB. And the third thing is f dash of x is equals to g dash of x for all x belongs to open interval AB. Then f of x is equals to g of x plus some constant. That's the difference. Okay, so you can start with the definition. You can define the function h. So I'm just giving you the hint for this case. You define a new function h from I to R by taking the difference of these two functions, f of x minus g of x, for x belongs to closed interval AB. So since sum of two continuous function is continuous, difference of two continuous function is continuous, okay, then clearly h is continuous on closed interval AB, h is differentiable on open interval AB, and derivative is 0 for open interval AB. Then you can apply the previous result that h must be a constant function, and h of x equals to c implies f of x and g of x are defined by only constant. Okay, right. Now the next result is also an application of mean value theorem, which is giving you one of the criteria to decide whether the function f is increasing on the interval or decreasing on the interval. So once you know the function is differentiable, then you can investigate the same. Okay, so let f be a differentiable on the interval I, and this is the if and only if condition. So the very first thing is, one wish to know what do you mean by increasing function and decreasing function, and I think I can mention here that if for increasing case I can mention, similarly you can go for decreasing. Okay, so if x1 less than x2 implies f of x1 less than or equals to f of x2, then we say that f is increasing on I. If it implies strictly less than here, then you will say it's a strictly increasing function. Okay, similarly, if x1 less than x2 implies f of x1 greater than f of x2, greater than equals to f of x2, okay, this inequality is reverse in, okay, means less than equal to will reverse in greater than equals to. If it is so, in that case we will say that f is a decreasing function, and if the equality sign not there, we will say strictly decreasing function. Okay, right. So if let f be a differentiable on the interval I, then f is decreasing on I if and only if f dash of x is greater than equals to 0 for every x in I. So means that if derivative remains non-negative over the entire interval I, then you can say f is increasing on I. Also, if f is increasing on I, then you can also show that the derivative will be non-negative for all x in I. Okay, then question will come is whether this will remain still true for the strictly increasing function. Okay, that we will look after. Okay, similarly result will happen for f is decreasing on I for decreasing function. If f is decreasing on I, if and only if the derivative is remain non-positive, or you can say negative, less than equals to 0 for every x in I. Okay, so let's look at the proof of this the part A, and similarly the proof of part B will go. Okay, so once you given with a function, to state that the function is increasing or decreasing, you can refer this result. Okay, right. So here are the steps. So let f is differentiable and increasing on I. So we are starting with the first case. F is increasing on I and f is differentiable. Then we will show that f dash of x is non-negative. Okay, so you have then f is differentiable and increasing on I. Okay, then what you can show this is this will be always true. F of x minus f of c by x minus c is greater than equal to 0 for every x in I, x not equals. So whenever x is not equals to c, there are only two cases, either x less than c or x greater than c. So x minus c is a negative, x minus c is positive here. Okay, now for x for now this case here, since f is increasing, so x less than c implies f of x is less than equal to f of c, and x greater than c implies f of c is less than equals to f of x. Now from here you can see f of x minus f of c, or f of c minus f of x is greater than equals to 0. C minus x is greater than equal to 0. So f of x minus f of c divided by x minus c is greater than equal to 0. From here also you can show that f of x minus f of c divided by x minus c is greater than equal to 0. It is irrespective of this order. Okay, it doesn't matter. So it will remain always true. It's greater than equal to 0. Now since we have already known that if a function is greater than equal to 0, okay, then its limit is also greater than equal to 0 for every x. So what is that is, so this is if in the limiting sense, what is this is f dash of c is greater than equal to 0 for every c. So you have started with a particular point c, okay, and you have shown that at that point it's non-negative. Because of the fact we are using the fact that f is differentiable and increasing on I, because we are using that fact that f is differentiable, where it is used, this limit does exist, and increasing on I because of this fact. Okay, you are using this fact. Okay, right. Now similarly you can show for decreasing function. Okay, right, then decreasing case it will be less than equal to 0. Okay, and that you can show that. Okay, right. So now look at the case in conversely. Okay, so means you have been given with f is differentiable and f dash of c is greater than equal to 0, then you are supposed to show that that function is increasing on I. Then you start with a point f2 point x1 and x2 such that x1 is less than x2. You need to show that f of x1 is less than equals to f of x2. Okay, so conversely, assume the condition holds true. Okay, now look at this interval x1 to x2. This interval x1 comma x2. Since f is differentiable on I, so f is also differentiable on this interval and also continuous on this interval, open interval x1 comma x2. So mean value theorem is applicable here. Okay, so therefore you will there will be exist a point c inside this interval, open interval x1 to x2, so that this condition holds because of the mean value theorem. Now since f dash of c is a point inside the closed interval ab, okay, and you know that you have already assumed that f dash of x is greater than equal to 0 for every x in I, so therefore this f dash of c is also greater than equals to 0. Moreover, this x1 is less than x2 means x2 minus x1 is strictly greater than 0. So x2 minus x1 is positive. So this is positive, f dash of c is positive, greater than equal to 0, and x2 minus x1 is strictly greater than 0. So the only then this will imply this is only possible then whenever f of x2 minus f of x1 is greater than equal to 0, and then hence f of x2 is greater than equals to f of x1 implies f is increasing on. Okay, so similarly for converse part for the decreasing also you can examine here. Okay, so once the function, if you look at the property of the function, if the function derivative is non-negative, okay, then on the interval close interval I, then you can certainly decide its behavior in increasing manner. Non-negative means increasing, and the non-positive means decreasing function. Okay, right. Now let's try to get the answer for strictly increasing function. Okay, so let f from I to R be differentiable. Prove or disprove that f is strictly increasing on I if and only if f dash of x is greater than 0 for every x in I. So that f is strictly increasing on I, then f dash of x is greater than 0. Or if f dash of x is greater than 0, then f is strictly increasing on I. So the one way is true. One way is f dash of this way is true. Means f dash of x is strictly greater than 0 for every x in I, then f is strictly increasing on I. So you can prove the similar manner. Okay, so f is differentiable and f dash of x is strictly greater than 0. Let f dash of x is strictly greater than 0 here for every x in I. So then you will have strictly increasing here. Right? For this case, if you instead of greater than equal to 0, if you have strictly greater than 0 here, then certainly it will be applicable here because f dash of c is strictly greater than 0, x2 minus x1 is strictly greater than 0. So this will imply f of x2 minus f of x1 is strictly greater than 0. So you will follow the strictly increasing. Okay, but in the reverse way, it is not true. Okay, so means if the function is strictly increasing, then f dash of x is strictly greater than 0. It is not true. Okay, for example, you can take here, so you can take example here, let f from R to R, okay, be defined by be defined as f of x equals to you can say x square, x cube, okay, and this function is strictly increasing, right? This function is strictly increasing. So f of x you can define on the interval, you can say here 0 to you can say 1, if you want to match with our condition here. Okay, so f is this function is strictly increasing, but f dash at 0, if you look at, that is going to be 0. Okay, so it is not strictly greater than 0. Okay, so still follow the greater than equal to 0. Okay, so this function is strictly increasing on I, but f dash of 0 is 0. So this is an example, counter example to disprove the fact that f is strictly increasing on I, then f dash of x is strictly greater than 0. Okay, right. Okay, so now let's also prove some of other important inequalities. These you can take as an exercise as well. So I'm just giving you the hint for the first one. Okay, so similarly you can follow for the second. So you want to show that e to the power x is greater than equals to 1 plus x for every x in R. So for x equals to 0, so inequality hold. Equality hold, right? E to the power 0 is 1. And right hand side is also 1. Okay, and 1 plus x is equals to 1 plus 0, that is equals to 1. So equality holds here. So for the case x greater than 0, what you can take is, you can take the interval 0 to x. And since this function f of x equals to e to the power x is differentiable and continuous, every nice properties are attached with this. So you can certainly apply the mean value theorem. Okay, so mean value theorem. So since f of x equals to e to the power x is differentiable, okay, in on R. Okay, so it is also differentiable on 0 to x. Then mean value theorem implies there exists some c which certainly depends on x in the interval 0 to x, such that f dash of cx is equals to you have e to the power x minus e to the power 0 divided by x minus 0. Right? Now, what from here, now how will you follow the result here? Since this, you know that e to the power x for x greater than 0. So e to the power x is greater than 1. Right? Whenever x is less than 0, e to the power x is less than 1. Okay. So you are going to use the fact that, so f dash of cx is nothing but e to the power some cx is equals to e to the power x minus e to the power 0 is 1 divided by x, and which is certainly greater than 1. So this will imply e power x is greater than 1 plus x if you solve it, because x is greater than 0, so you can certainly multiply x on both. Similarly, for the result for x less than 0, you can use the interval x to 0, and then you will use the fact that e to the power x is strictly less than 1 for x less than 0. Okay, right. Now, in the second case, that sin x function is continuous and differentiable, and use the fact that the derivative of this function, that is cos x, that lies in the interval minus 1 to 1. The values lies in the interval minus 1 to 1 for the sine, the cos function, right? And use that fact and apply the mean value theorem in the similar fashion. Okay, right. So this second problem you can, or else if you are not that you can also refer the book. The proof is available there as well. Okay, right. Okay. So before going this first derivative test, let me also give you another important application of you can say in particular Rolle's theorem. So you can say application of Rolle's theorem. So here was, let f from I to R I is equals to closed interval AB, and first condition is f is continuous on I. Second is f is differentiable on upper interval AB. Third condition is f of A is equals to f of B. The at endpoints, they are equal. Then there exist, and that is equals to, we have started with the they are 0. Okay, then there exists C in open interval AB such that f dash of C is 0. So if you look at this back, okay, so what it tells you is between any two zeros of f, so f of A and f of B are two zeros of f. If there are two zeros of f, and that satisfies, the function f satisfies the condition of Rolle's theorem, that f is continuous on the closed interval AB and f is differentiable on open interval AB, and that at the endpoints, the endpoints are nothing but the zeros of the function f. That will actually locate the zero of its derivative as well. Okay, so what it tells you is that between any two zeros of f, at least one zero of its derivative f dash. Okay, so it gives you guarantee that there is at least one zero of f dash once you locate the points A and B, which are such that f satisfies the condition of Rolle's theorem over the interval A. Okay, so it locates the root of the derivative of the function. Okay, so what it says is it locates the roots of the derivative of f. Indeed, it guarantees that there is at least one zero of, it guarantees that there is at least one zero of f dash between any two successive zeros of f. Okay, right. Now, another important result also, or you can say as again, it's an application of mean value theorem. You can actually use the first derivative test for finding the maxima or minima of certain function. Okay, right. So this purely follows by using the definition of the derivative. So I may skip the result here. Okay. So let f be continuous on the interval I and let c be an interior point of I. Assume that f is differentiable on open interval a to c and c to b. We don't know about the f dash. Okay, so we don't know f dash, whether f dash of c does exist or not, but we know that f is differentiable on this a to c and c to b. Okay, if there is a neighborhood such that f dash is changing sign, okay, so f dash is changing sign over the interval, it means from c minus delta c to c plus delta. So we are talking about, if you go back and check, the definition of limit was entirely on 0 less than mod x minus c less than delta. Means this is a union of c minus delta to c union with c to c plus delta. These two intervals are included except the point c. So again, I'm telling you, purely it's finding a depends on the derivative. Now you can write in the limit, okay, and then you can apply the result. So if there is a neighborhood such that this happens, so f is changing sign from positive to negative, then you can say that f has a relative maximum at c. Means from here it was positive and it is here negative. So if it is in reverse manner, means from here it is negative and here is positive in this interval, if you are able to justify, okay, that if f is changing sign over this interval, then f has a extremum. Okay, that's for sure. Now to decide its relative maximum at c or its relative minimum at c, okay, that is going to be, so if we're talking about relative maximum, it is changing sign from positive to negative. It is very easy to remember. Okay, for relative minimum at c, it is also determined from negative to, okay, it's in reverse. Okay, so if there is a neighborhood, so we don't know whether if f dash of c exists or not, we don't know. This is the first derivative test for checking whether it has relative maximum at c or not. Okay, similarly, if there is a neighborhood such that f dash of x is changing sign from negative to positive over these intervals, then f has relative minimum at c. So it's purely based on the writing the definition of the derivative in terms of limit, and use the fact that it is less than equal to 0 on this and it is greater than equal to 0 on this, then you can show that f has a relative minimum at c. Okay, so we don't know that f is f dash of c exists or not, but it is c, f is defined on c. So you can show that here f of, in this case, you can show that f of x is less than f of c. Okay, for all x. Okay, and here you can show that f of relative minimums, f of c is less than f of x. Okay, so that you can show. Okay, right. And also maybe you will be able to use the fact that if the derivative is greater than equal to 0, okay, then it is behavior is increasing over this interval and it is decreasing over the interval. Okay, so I'm skipping the proof for this case. Okay, there's no need for this, right? So now another important here is, suppose the derivative exists. Okay, let I be an interval and let f is from I to r, and let assume that f has a derivative at c. Then if f dash of c is greater than 0, so then there are two possibilities, there are three possibilities actually. So for the case, so there are three things. F dash of c exists, so that is either equals to 0 or greater than 0 or less than 0. Now if it is greater than 0, then you will be always able to identify a neighborhood of c, okay, or an interval, you can say in interval such that f of x is greater than f of c. Okay, means what is the meaning of this? Okay, means you are able to, so here x belongs to c is less than x. Okay, x belongs to c is less than x, and f of c is less than f of x. Okay, this is purely again, you can this is purely again the you are going to use the fact that f is increasing and decreasing. You know, you have already shown that if f dash of x is strictly greater than 0, then f is strictly increasing. Okay, so if f dash of c is greater than 0, then it's strictly increasing over the interval c to, we can say c to c plus delta. So if f, okay, over the interval, right? And now if f dash of c is less than 0, so what here is, so previously we have talked about on the interval that it is strictly greater than 0. Now you are talking about at a point it is strictly greater than 0. That is, there is a difference. Okay, right. So if f dash of c is greater than 0, then there exists, there we are always able to find delta such that this happens. So what it tells you is f of c is not maximum. Okay, f of c cannot be maximum here, relative maximum you say, right? Because you will find the values of you will find the point in I such that f of x is greater than f of c, means they are sitting on the right of it. Similarly, for the case f dash of c is less than 0, then also you can able to find in neighborhood, or you can say part of neighborhood of c such that f of x is greater than, again it will, in the case, means if you're thinking that if f dash of c is less than 0, then you will be able to find out, the still result will not be hold true. Okay, so again its point is again depends on its proof is again depending on the definition of the limit at means f of f dash of c, you write it in the limit and then use the fact. Okay, so the proof is not necessary here. So what you need to understand is, if f dash of c is not equals to 0, is either greater than 0, or if it is greater than 0 or less than 0, then it will not be it is not going to be the in either case it is not going to be, sorry, relative maximum. Okay, right. So we are going to use this lemma, we are calling this as lemma. Okay, so there is difference between calling lemma propositions, okay, and theorems. Okay, so lemma is always designed to establish some important results. And what is the important result is intermediate property of derivatives. So like we have we have already looked at intermediate value theorem for continuous function. Okay, so if you take any value between f of a and f of b, then you will be always able to identify a point C on the interval AB such that f of C is equals to k. So similarly, for the case similarly, the property for the derivative also exists. Okay, so that we are going to take here. Okay, so which is as follows, and also known as Darboux theorem. Okay, so if f is differentiable on closed interval I, and if k is any number between f dash of a and f dash of b, then there is at least one point C in upper interval AB such that f dash of C is equals to. So in the case of continuity, we have defined the function. We have used the fact that Bolzano's property there, right? And we have defined the function f of x minus k, and then we have look at the proof. Okay, so here also we are going to create an artificial function. Okay, here also we are going to create an artificial function which is going to be, so we have, so this k point is any number, so f dash of a is less than k less than f dash of b. Okay, so k is any real number which is such that f dash of a is less than k less than f of b. Okay, now you will define, we will create an artificial function g from I to r by g of x is equals to some k times x minus f of x, so that we can talk about f dash of a minus k is less than 0 and f dash of b minus k is greater than 0. We are going to use that fact. So, and then it will be combination of, now the proof is going to be combination of the results what we have derived earlier, law called interior extremum theorem and the above lemma. Okay, that we are going to use here. Now see, if you define this artificial function g in this way, so since function is differentiable on I, and you know that polynomial is also differentiable on R, entire R. So this function is differentiable on I. Okay, now since I is closed interval AB and G is differentiable, means G is continuous. So maximum minimum theorem tells you that G attains its absolute maximum, right, on the interval I. Means you will be able to identify a point, say C in I, such that G of C is the maximum. Okay, similarly for the minimum as well, you can, because the function is continuous on a closed and bounded interval I, then it attains its absolute maximum and absolute minimum in I. So you will be able to identify the points. Okay, now, okay, so let's look at the proof here. So let k belongs to R be such that this happens, and define G from I to R by this. So G is differentiable on I, also I is closed and bounded. So G attains maximum minimum theorem tells you that G attains its absolute maximum at some point, say C in I. Okay, now, and you know G is differentiable on I. So we are going to show first that C is going to be an interior point. It cannot be the boundary point. That's very first thing. Okay. This is going to be because, so what is g dash of x? If you try to get here, this implies g dash of x is k minus f dash of x. Now, check the g dash of a. What is g dash of a? G dash of a is k minus f dash of a. And you know that this f dash of a is less than k. So g dash of a is greater than 0 and g dash of b is strictly less than 0. And just now you have observed from previous result that if at point derivative exists at g dash of a is greater than 0 or g dash of a is g dash of c is less than 0, then it will not attain its relative maximum at c. So only possibility is g dash of c is 0. then okay, that's the only possibility, right? And this will discard the fact that C is neither equals to A and C is not equals to P. So maximum minimum theorem implies G attains its absolute maximum at some point, say C in I. Further, you note that G dash of A is greater than 0 and G dash of B is less than 0. So this the lemma what we have just seen is says that C cannot be neither A nor B, because we are able to identify a delta such that over which this G of A is sitting on the left of many values of G of X. Okay. Similarly, for the case G dash of when G dash of B is less than C. Okay. So C, but C is a point where the G attains its absolute maximum. So C will neither A nor B. So therefore C is an interior point of interval I. So now since C is an interior point of interval I and G is differentiable on I, or G is differentiable on I. Okay. Further, G has relative maximum or relative extremum point, relative extremum at C. So that implies G dash of C must be 0. And here is the proof over now. So C is an interior point of I now. So then interior extreme theorem implies that G dash of C is 0. But G dash of C is nothing but F dash of C minus K is equals to 0. So this implies F of F dash of C must be equals to K. Okay, right. So this is about the differentiability of extreme functions of single variable. Okay. Now other applications are here as well, which are such that expanding function by means of power series. Okay, means you are given with a complicated function that is not easy to work with it. Okay, we will not be able to work with it. That's too complicated. So what you can do is you can get an equivalent approximation of this function in terms of as a polynomial, you can say. Okay, maybe a large degree polynomial. Okay, so power series is a series, okay, containing infinitely many terms, and in terms of x to the powers, you can say x square whose that is going to be in terms of 1 comma x square comma x cube and so on. So summation of over this. So that we have to look now. Okay, so that approximation of functions by means of power series. So because that requires later on the differentiability of function. Okay, then only you can get those things nicely. Okay, so now we are going to look at the approximation of function. So the very first thing, so a power series is a series of the following form. So we have already learned the infinite series, so there is no point like that. This is going to be very clear. Okay, so means in terms of polynomial, it's kind of a polynomial approximation. So if you approximate by linear polynomial, linear approximation. If you're going to approximate by 2-degree polynomial, it's a quadratic approximation, cubic approximation, biquadratic approximation, and so on. Okay, so certainly whenever you are talking about an infinite series, this is a part of infinite series. It's a special part, you can say infinite series. Okay, so this is here. So certainly we need to worry about its convergence. Okay, and you know that the convergence is entirely depends on the partial sum. Okay, so therefore, and the very other point is if x equals to 0, suppose x is equal to 0, so then this series has convergence guaranteed at x equals to 0. So we don't worry, we should not be worried about the point x equal to 0. We should be worried about the points which are distinct from 0. Okay, so that's very first thing. Now for the same, we are going to define an interval of convergence. Means if it converges, so where will it converge? Okay, means for what values of x this will converge, means what by meaning of convergence means this infinite sum will have some meaningful name attached with it, means it give you some finite values. Okay, right. So for identifying the convergence interval, you can say interval of convergence or convergence interval. So you can define the radius of convergence for this case. Okay, so R is equals to, what is the radius of convergence is going to be defined as R equals to limit of mod by an plus 1. So this absolute value, you take the coefficient of x to the power n. Okay, so this will be entirely depends on this. Okay, so look at the part here. So if I consider this power series summation a n x to the power n equals to 0 to infinity. Okay, so let's summation n equals to 0 to infinity. So this is xn sequence. Okay, sequence. This is a sequence generated by this, right? The corresponding sequence is an times x to the power n. So if you look at the nth term, so I will say this xn is equals to this power series is generated by this corresponding sequence. Now you can talk about xn by xn plus 1. Okay, xn by xn plus 1. So that is going to be as an x to the power n divided by an plus 1 x to the power x to the power n plus 1. And this implies mod of xn by xn plus 1 is equal to mod of an by an plus 1 times 1 by mod x. Right? So now if you recall the ratio test from the previous your sequence criteria and all, so you justify here that whenever this is going to be there, okay, so it entirely depends on this. You can certainly get the values of this 1 by mod x should be less than 1, something is there. Okay, so if you recall that ratio test, then you can certainly attach some meaning to this R. Okay, so this is the point here to explain here. Okay, we have already seen that limit xn plus 1 by xn is equals to 1. Then there is no conclusion with less than 1, greater than 1, that convergence and divergence, we can look after that one. Okay, so this is why this name is attached here. The radius of convergence means you are going to obtain mod x less than R. So the radius of convergence is this, provided this limit should exist. So that's the very first thing, important thing, that radius, this limit should exist. Then you can define the radius of convergence by this limit. And minus R to R is called the interval of convergence. Now, if R is equals to infinity, means it is going to be convergent for all values of x. If R is equals to 0, suppose limit is 0. Okay, 0 is less than 1. You can go and check. So 0 is less than 1. So if R is equals to 0, then you have this is only convergent for x equals to 0. Okay, for R is equals to okay, so you can look at some examples now. Okay, let's look at some examples. So let's take one example, that summation, you have n factorial times x to the power n. Okay, so if you try to find R here, so what is that is, so that is limit of that so and so. So now, so before finding R, so let's find an by an plus 1. So that is going to be n factorial divided by n plus 1 factorial. And that is equals to 1 by n plus 1. And which tends to 0 as n tends to infinity. Okay, so this implies in magnitude as well, magnitude sense as well, because this is our non-negative term. So mod, and if you take mod, that still will not be a problem. So this implies r equals to 0. So it means that this will only converge for x equals to 0. Okay, so instead of this, now suppose this summation n equals to 0 to infinity x to the power n by n factorial. So what can you tell about this here? So you have, this is an by an plus 1. That is going to be, you have, this is going to be 1 by, so you have n plus 1 factorial by, right, n factorial, and that is equals to n plus 1, and which tends to infinity as n tends to infinity. So properly divergent. Okay, and so r is infinity means it's going to be converged on for all values of x. Okay, and in other words, sometime also if it is converged for every value of x in r, that we also say sometime entire function. Okay, entire function. So this, you know, this is the expansion of e to the power x. Okay, so similarly you can show that the power series for sine function, cosine functions that are also converges for every values of x. Okay, by just deriving this here. Okay, and so now the another important result related with the convergence of the power series is as follows. So if a power series is convergent for x equals to c, suppose at x equals to c it is converges and c is non-zero, then you can certainly show that it converges absolutely for all mod x less than mod c. Okay, so that will be sure. So if you are able to show that convergence for x equals to c, for example, this here, suppose x equals to 1 here. So if the series is converges for at x equals to 1, this is also converge for mod x less than, it is absolutely converge for mod x less than 1. Okay, so there is so you can start with a particular, and you can get the interval of convergence, means part of interval of convergence for the values of x. Okay, convergence. Okay, similarly, if you are able to find that the series diverges for x equals to d, then it diverges for mod x greater than mod b. So if you look at here, so you can take x equals to 1. Okay, or you can take any x equals to half here. Okay, doesn't matter. Okay, so then you can show that this is going to be diverges for at that value, any x greater than 0 value. So it is going to be absolutely diverge for mod x greater than 0. Okay, similarly for you can say this is going to be right, mod x is greater than mod b we are talking about. So similarly for x equals to negative value. Okay, so we can make guarantee about convergence, absolute convergence. Okay, absolute convergence in some region. Once you are able to identify that the corresponding series is convergent. Okay, for you can say for at certain point, then you can certainly find out some interval of some part of the interval of convergence, you can say. Okay, and what is the why it is required is because once you have this privilege that this converges absolutely for all this and it diverges for this. Okay, suppose the series converges absolutely in this way. Okay, so the things what you have learned so far, differentiability means if you can differentiate this, you can integrate this, means term-wise integration, term-wise differentiation. Okay, how many time doesn't matter, infinitely many time you can do. Okay, you can differentiate as many times as you wish. and you can integrate as many times as you wish. Okay, 2-time integration, 3-time integration, 4-time integration in this particular interval. Okay, this where you are sure that this converges absolutely for this interval. Okay, so this term-wise integration and term-wise differentiation is allowed. Okay, when in the interval of convergence for the power series. Okay, on the other hand, it is not allowed for this. Okay, so that's a important thing attached with this convergence. Okay, right. So for deciding the interval of convergence, you can certainly look at the point. You can certainly go for the definition. Okay, that r equals to that limit. Okay, try to identify that limit. That limit is not that much difficult. You have already learned too many concept. Okay, for finding the limit of certain sequence. Okay, so an by an plus 1 is again a new sequence. Okay, so that you are going to do, and you find the r, and then you can identify the interval of convergence. So where it does converges absolutely, then you are going to you are allowed to do term-wise integration, term-wise differentiation for the power series. Okay, right. Now we are going to, so this is here, so some of the comments here. The power series always behaves exactly one of the following three ways that already understood. It converges at x equals to 0 and diverges everywhere else. It is possible. So we have already seen the example summation n factorial time x to the power n. That we have already seen. Second thing is, there is a positive number c such that the series diverges for mod x greater than c but converges absolutely for mod x less than. It may or may not converge at either of the endpoints x equals to c and at x equals to minus c. That also possible. Okay, so at x equal to c or x equal to, so it may possible that there is a positive number c such that the series diverges for mod x greater than c but converges absolutely for mod x less than c. It may or may not converge at either of the endpoints. So for example, you have, this is going to be summation, okay, that x to the power n. So then you can certainly, you have already seen that this is converges only for mod x less than 1. Okay, but for x equals to 1, it diverges. Okay, and it diverges for mod x greater than 1. So you can certainly tell about whenever x equals to 1, it is diverges, is properly diverges. Okay, now because of the previous result, what we have just now seen, that therefore it is diverges for mod x greater than 1. Okay, and you can also show that mod x less than 1, it converges. So it may or may not converge at either of the endpoints at x equals to c and at x equals to minus c. So it does also not converge at x equals to minus 1, and it also not converge at x equal to 1. Okay, and third thing is, it converges absolutely for every x. Okay, so it converges absolutely for every x. So you have already seen that summation x to the power n by n factorial. You have already seen that it converges absolutely for every x. Okay, so in the case of 2, where you are identifying some stage here, right, in other words, it is a stage. Afterwards it converges, and afterwards it will not converge, and it will converge in this interval. So that point is also called the radius of convergence. Just now we have learned this mod x less than r. So that's why whenever you are going to write the radius, find the radius of convergence as r, you are going to write that the power series will converge only in the region less than r. You are not going to include equality sign here. So it may or may not converge in this, but safer side, you can say, is strictly less than r. You can discuss at equals to r separately, equals to r or minus r. Okay, so this point r is called the radius of convergence of this. So only these points are possible. Right. Right. So now whatever we have discussed so far, okay, so whatever we have discussed so far, you can generalize the result for, in terms of, instead of x to the power n, you can also generalize the result for n equal to 0 to infinity a n time x minus a to the power n. Means in the neighborhood of a, you can say it. We are previously talking about in the neighborhood of 0. So these two series, about these two series are almost identical, because at x minus, you can replace x by y plus a, or you can say x by x minus a, you can replace. Okay, so you can take x minus a by y, then it will be entirely this series only. So x equals to y plus a. Okay, so so convergence or divergence you can talk about in the similar manner here. So now instead of x here, so you have, this is x minus a equals to c. You replace at everywhere whenever x is there, here you replace x by x minus. So instead of this, radius of convergence is mod f less than mod c, that will be mod x minus a less than mod c. Okay, so you can certainly talk about this series as well by looking at this. Okay, right. Now you can look at the interval of convergence of this. Okay, so you have, this is an by an plus 1 is equals to n plus 1 by n. If I'm not wrong, this is an is 1 by n. So 1 by n divided by 1 by n plus 1, and which tends to infinity as n tends to infinity. So properly divergent series. So r is equals to infinity means that this series converges for mod x less than infinity, means for all values of x. Okay, now for this case, you have, this is going to be, you have to write in terms of x minus a. So I can write it as summation n equals to 1 to infinity 2 to the power n by n square times x minus 5 by 2 to the power n. Now you work out with this 2 to the power n by n square. So an by an plus 1. That is going to be 2 to the power n by n square into n plus 1 whole square divided by 2 to the power n plus 1. Right? So this is going to be, this is going to be 1 by 2 times n plus 1 by n whole square. Now you know that this n plus 1 by n goes to 1 as n tends to infinity. Right? So its a square also goes to 1 square. You can use the fact that x into y, the product of two sequence converges. If both the sequence converges, product will converge to the product of their limits. So this will converge to 1, and so this will converge to 1 by 2. So the series, so radius of convergence is 1 by 2. So it will converge for the values mod x minus 5 by 2 is less than 1 by 2. You can find the interval of convergence. So this will implies minus 1 by 2 less than x minus 5 by 2 less than 1 by 2. You can find certainly this is going to be 2 less than x less than 3. So in the interval 2 to 3, it will surely absolutely converge. Okay, and at point x equals to 2 and x equals to 3, you can certainly talk about this. So for x equals to 2, what will happen? So at x equals to 2, going to be 4 minus 5, so minus 1 to the power n by n square. You can show by using p test that this is going to be converges. Okay, because p is greater than 1, 2 is greater than 1. Okay, similarly for
in the previous example also it would tend to 1, n plus 1 by n.
Yeah, this tends to 1, so this certainly this is going to be less. Yeah, thank you. So because I have understood this is going to be remaining only n plus 1, so that's why it happens. Okay, now similarly for at x equals to 3, so at x equals to 3, again you can talk about the p test, and you can show that at x equal to 2 and at equal to 3, this also converges. Now the Taylor's theorem about the point x naught, and this will give you the polynomial approximation for a given function f about in powers of x minus x naught. Okay, and here you can indeed you can identify what are the coefficients an here. Okay, so if this Taylor's theorem, this is Taylor's theorem. So if the remainder will be tending to 0 as n tends to infinity, then you can write in terms of power series, you can say. And therefore this e to the power x, sine x and cos x, these are written in the Taylor series format. Okay, right. So let me this, because this is a very non-result to you, so I don't think so there is any problem in delivering this Taylor's theorem, that let n is a natural number, let I is a closed interval, and suppose f is such that this is continuously differentiable n times, means f up to first derivative, second derivative, nth derivative, all are exist and continuous. Okay. Okay, and also assume that fn plus 1th derivative exists on AB. Then you can expand this f in terms of this. So if you if I want to write a compact form, this is going to be summation k equals to 0 to n x minus, so you have, this is going to be f kth derivative at x naught divided by k factorial time x minus x naught to the power n, k, x minus x naught to the power k plus rn x comma x naught. This is a remainder after n terms, okay, which is given by this formula, and which is an application of mean value theorem that you can just refer the result. Okay, this is again going to be an application of mean value theorem. Okay, so this is called, this Pn of x is called the polynomial approximation of f of x, and this is called the error in that approximation. Okay, and then if you are able to show that, so if you are able to show that this tends to 0 as n tends to infinity, then you are through. That you can write in terms of plus dot dot dot, means infinitely many terms, and they are having some meaning. And what is an here is, ak here is f kth derivative at x naught by k factorial. So for k equals to 0, zeroth derivative is nothing but the function itself. Okay, right. So this is we are going to look now. Okay, so this is here, so it's clearly here mentioned that Pn of x is the polynomial approximation n degree polynomial. It's called the Taylor's polynomial of degree n about the point x naught, and this is called the referred as the remainder form, which is also known as Lagrange form of the remainder. Now see, look at this. So if suppose fn plus 1th derivative is bounded, okay, suppose fn plus 1th derivative is bounded, means bounded by m. So this certainly is a constant, some fixed constant. Okay, and you can show that this x minus x naught to the power n plus 1 by n plus 1 factorial tends to 0 as n tends to infinity. Right? Because this is the part of, right? Because this is the part of the infinite series, and you know that if that converges, then its nth term tends to 0. If you recall, summation xn converges. Okay, if summation xn converges, then limit of xn is 0. It's a necessary condition. Okay, and then this you can show that summation x minus x naught to the power n plus 1 by n plus 1 factorial converges. Okay, so it is only required that n plus 1 of the derivative is bounded. Okay, then you can write that as infinitely many times. So you can now work over the polynomial approximation is e to the power x, sine x, cos x, and so on. Okay, right. So now this is a remainder estimation theorem. You can say, okay, so this is what I was talking about. So suppose n plus 1th derivative is such that it is bounded, and it is bounded by m time r to the power n plus 1. So r is here some number, doesn't matter. Okay, doesn't matter. It is a real number, you can. Okay, but it is positive because it's mod here on the left side, so it must be positive. R must be positive number. Okay, m is also positive. Okay, so if it is so, then you have the error estimate also is bounded. Okay, so you can show that this is going to be summation. You can show that r time x minus x naught, this is mod. You can say that to the power total to the power n plus 1 by n plus 1 factorial. If you recall, this is nothing but the e to the power r time mod x minus x naught. This expansion of this only. Okay, and that converges you can show by using the converges for what values of x at x equals to x naught. No need to look at. Okay, what is the radius of convergence for this series? You can find out that by limit. Okay, then you can show that this is converges for every value of x. Okay, so since this infinite series converges, so definitely this tends to 0 as n tends to infinity. Okay, so if the condition above hold and all the other condition of Taylor's theorem are satisfied, then the series converges to f of x. Okay, so n tends to infinity, then it tends to 0. The remainder estimate is tending to 0. Okay, right. So these examples are going to be shown. Okay, maybe I will supply some PDF file for this example. So Taylor approximation of e to the power x. So if you take P1 of x, is going to be the linear approximation. E to the power, so y e to the power x equals to 1 plus x. If you take, that's going to be the linear one. Okay. Now if you take, this is approximation. If you take P2 means 1 plus x square by 2. Okay. So it will be little smooth. Okay. So if you increase, that's going to be y equals to P3 of x, then y equals to P5 of x, and y. So this is the actual curve y equal to e to the power x, which is plotted by using some, let's say, MATLAB tool. Okay. So this actually, so this what it shows is in the limiting sense, it converges to the curve. Okay. This is one fundamental example of Taylor approximation of e power x. Similarly, for sin x function. Okay. For sin x, you know, so for linear approximation, sin x is x. For quadratic, there is no quadratic, only odd degree polynomial. So x minus x cubed by 3 factorial. Okay, that's going to be this blue line. Okay, the blue curve. Okay, then you will have this is x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial. That's the P5 of x. That's going to be difference. And so on. So P7 is almost mirror to the sine curve. You can see here. Okay. Similarly, for you can have this is ln of 1 plus x here. Okay. Right. So that we are going that is a ending of this. You can say differentiability one. So if you have any question, so you please ask.
So there is doubt in yesterday's lecture, interior extreme theorem. In that we have proved that f dash must be equal to 0, and we disproved that it can't be greater than 0 or less than 0. I have doubt it would be less than 0, then how we can prove it similarly as greater than 0?
Here.
In these slides you have put us like that if
Wait a minute. Here it is this.
Yeah, next slide. We have disproved that f dash of c can't be greater than 0. And we that similarly we will say that f dash of c would be less than 0 also can't. we can prove in similar way. If we would prove, then f of x minus f of c upon x minus c would be less than 0, and from there we can say that f of x is less than f of c, and then we can't contradict that f of c is relative maximum. We change the sign of x and c, like here it is like x is greater than c, and then we can say that c is greater than x. This proved.
See here, we have used the fact that this is f of x minus f of c by x minus c is greater than 0 in the limiting sense, because f dash of c is greater than 0. If you are using that, we are starting with this, then there exists a delta such that this happens. Okay, now for the case you can say, see, x is not equals to c. Whenever x not equals to c, this is greater than 0. Okay, in the some deleted neighborhood of c. Now you look at the case x greater than c, means x minus c is positive. So that will certainly force us to have f of x minus f of c is greater than 0, means f of x is greater than f of c. Okay.
Yes.
Okay. Now in the next case, if suppose you are going to use less than 0. Okay. Suppose you are going to have this is less than 0. So this is less than 0, but this is less than 0 for x in this. Now similarly for x greater than c. Okay, then f of x minus so you cannot go with the x minus c is you can say x greater than c.
Yeah,
Okay,
so
because
then we need
okay,
to
then
change
you,
condition.
yes, x less than c.
We can
So
assume that things.
yes, may see, because it is true for all x not equals to c. So it's true for x less than c and x greater than c. Okay, so for x less than c, x minus c is negative, and to make this overall positives, f of x minus f of c also must be negative.
Okay.
Okay, so this is the fact here. Is this you are supposed to identify some values in I, so that they are sitting on the right of f of c.
Okay.
Okay, yeah.